In this video, we're going to take a look at Raoult's law. And so we first need to start off and talk a little bit about phase equilibrium and what that is. So a phase equilibrium is a dynamic equilibrium between different physical states of a pure substance in a closed system. For example, if we put water, liquid water, into a container and then we created a closed system by putting a stopper on it, eventually it will establish an equilibrium between its liquid state and its gaseous state. So initially will start to evaporate and that rate stays consistent. And then once we built up enough vapor, we're going to start condensing. So the rate of condensation is going to go up, and then dynamic equilibrium is established when the rate of evaporation is equal to the rate of condensation. So vapor pressure then arises because it's the pressure exerted by a vapor on its liquid when the system is at equilibrium. So when the rate of condensation is equal to the rate of evaporation. For a pure liquid, the vapor pressure is going to depend on the nature of the liquid as well as the temperature. Whereas if we have a mixture of liquids, it will depend on the nature of the liquid and the temperature for both liquids. And it's also going to depend on how much of each of the liquid is present. So this is really important to understand because then that gives us information about fractional distillation and how we can purify different drugs and medications if we know how much of each is present within the vapor itself. So getting into Raoult's law then, we need some definitions to start off with. First, the first one is volatile. That just means something that evaporates readily. An ideal solution is a mixture of liquids in which the intermolecular forces are the same as they are in pure liquids. A mole fraction for component A, for example, the mole fraction of A would be the moles of A divided by the total number of moles. And then finally, our last definition we need is the partial pressure. So that is the pressure exerted by a particular gas in a mixture of gases. It's defined as the partial pressure of A is the mole fraction of A times the total pressure, where the total pressure is equal to the sum of all of the component partial pressures in the system. Okay, so what does that have to do with Raoult's law? Well, Raoult's law says that the partial vapor pressure of any volatile component of an ideal solution is equal to the vapor pressure of the pure liquid multiplied by the mole fraction of that liquid in solution. So PA is the partial vapor pressure of A is equal to the mole fraction of A times the vapor pressure of pure A. So we can figure out the partial vapor pressure of A if we know what the mole fraction and the pure vapor pressure is of A. So this can be a very, very useful equation. So let's look at an example here, and we want to look at given vapor pressures of pure hexane and heptane at 25 degrees Celsius are 20.5 and 6.10 kPa. So that's going to be the pressure naught. So that is our pure substances. We want to calculate the vapor pressure of an ideal solution containing 4 moles of hexane and 4 moles of heptane. First off, we need mole fraction. So let's call hexane A and we'll call heptane B, just to make this easier. So the mole fraction of A is going to be the moles of A, which is 4, over the total moles. So 4 plus 4. So that gives us a mole fraction of 0.5 of A. And then the mole fraction of B is the same. And that's just because they're both 4 moles here. All right, so now we can figure out the vapor pressure with respect to A. So that's going to be the mole fraction of A times its vapor pressure of the pure liquid. So we're going to take 0.5 and then A is hexane. So that's given to us at 20.5 kPa. So that gives us a partial vapor pressure of 10.25 kPa. And then if we do the same for B, that's going to be 0.5 times 6.10. So that gives us 3.05 kPa. And that means that the total pressure of this system, we're adding both of the partial pressures. So that gives us, if we take 10.25 and 3.05, that gives us 13.3 kPa. So the total vapor pressure of the solution is 13.3 kPa. If we wanted to know what the mole fraction of each is in the vapor, we could work backwards here and figure out, for example, the mole fraction of the vapor of A is just going to be the pressure of the hexane, so the 10.25 that we calculated here, so the PA, over the total pressure, so the 13.3. So that gives us 0.771. And then we could do the same for the vapor of B, and that gives us 0.229. So that's 3.05 divided by 13.3, which gives us 0.229. So that tells us that there is pretty much 77% hexane and only 23% heptane in our vapor. So really helpful to know, because then we know when we're doing fractional distillation how much of each sort of thing we are getting when we are separating liquids using that technique. So just kind of briefly talking about boiling points then of a liquid. A liquid's going to boil when its vapor pressure is equal to the external pressure. So the normal boiling point of a liquid is going to be the temperature at which the vapor pressure of the liquid is 1 atmosphere, because that is generally what our external pressure is. The more volatile a liquid is, means it's going to have higher vapor pressure. So that means it's going to have a lower boiling point, because it's going to hit the external pressure point quicker than if something is less volatile. But when we add something to a volatile solution, so if we add a non-volatile solute into the solvent, the boiling point's going to change, and that's because the vapor pressure of the mixture of the two liquids, so the mixture of the two liquids, is going to vary with the composition. And the boiling point then is also going to vary with the composition of the mixtures. So we can look at this then as a boiling point composition diagram for an ideal solution. And if we take a look here, we have a mixture of pure A, and pure B. Keep in mind here, A is more volatile because it has a much lower boiling point than B does. Now, if we were to take a mixture of these and an ideal solution of these two components, A and B, we would get this boiling point composition diagram. The red line here, so this one here, shows how the boiling point changes with composition. And the blue line is the vapor, and that's showing how the vapor with which a particular mixture is in equilibrium. So if we were to consider that we had a mixture in which the mole fraction of A was 0.3 and the mole fraction of B was 0.7, so down here are scales for mole fractions. You can see A goes from 0 to 1 this way, and then B goes from 0 to 1 the opposite way. So if we had this mixture of 0.3 and 0.7, and we follow the graph or up to the red line here, that tells us that we're going to have and see a boiling point of 81 degrees with this particular mixture. Now, if we were to go horizontally over to the vapor line and then follow that back down, that tells us the vapor has a composition of a 0.6 mole fraction of A and a 0.4 mole fraction of B. So this is really important with fractional distillation, and we'll explain that in another video. So that is Raoult's law and how it applies to boiling point composition diagrams. That's it for this video. We'll see you in the next one.